our goal was basically to construct a uniform measure on the closed interval from 0 to 1. So we want a notion of having the same probability or the same likelihood of hitting or choosing any point on the interval from 0 to 1. So basically, if we try to assign probabilities to the singletons, so those are the subsets of big omega that contain one element. So what should we assign to these basically singleton subsets of big omega? So what should be this probability here? So we have two options. So the first option is that we give a positive probability, so epsilon, which is greater than 0, right? But here is the problem. If we want a notion of uniformity, a uniform probability measure, then basically all the singletons will be assigned the probability epsilon, which is strictly positive. And so if you take a countably infinite collection of those omegas, so basically you take the countably infinite union and you find its probability, it will be the sum by the axioms of a probability measure. And so you will have to sum the probabilities. So you take a positive number, no matter how small, and you add this positive number to itself an infinite number of times, and you will get infinity, which is not accepted because we want the probability of big omega itself just to be 1. You cannot have a probability more than 1. Okay, so this is rejected. So what we will do is that we will assign to the singletons the probability that is equal to 0. And automatically, if we assign to the singletons the probability 0, it means that if you take a countably infinite collection of those guys, then the probability will be the sum of zeros. You sum 0 plus 0 plus 0 plus 0 plus 0 and so on, you will get a 0. So automatically, when you take the singletons and assign to each guy the probability 0, automatically any finite or countably infinite subset of the closed interval 0 to 1 will get the probability measure 0. So this means that, if you are interested in having a uniform measure on 0, 1, then the probability of, let's say, choosing a rational number, then this probability is equal to 0 automatically. So if you choose randomly a rational number from 0 to 1, by our argument here, this probability should be 0, despite the fact that rational numbers are dense. They are everywhere from 0 to 1. There is no part of 0 to 1. You cannot basically set any open interval in 0, 1 and find it devoid of rational numbers. The rational numbers are in all basically intervals you can think of. So yes, despite the fact that the rational numbers are dense, despite this fact, still we have the probability of the rationals, or actually, so this is a more general statement, if you take any countably infinite subset of big omega, its probability will be 0. So last lecture, someone asked this question, which is, so does this mean that the probability of big omega is 0? If we assign to the singletons the probability 0, is this true? Is this statement true? So let's try to write big omega in terms of the singletons. So what is big omega? So big omega will be a union, okay, and then you take R, okay, so it's composed of R, and R is, what is the index? So we want to index every point on the closed interval from 0 to 1. Well, basically this index is a real number. Okay, so it is the real numbers from 0 to 1. You cannot use a natural number because basically intervals, they have the same cardinality as R, and R is strictly larger than the natural numbers or larger than any countably infinite set. So basically omega is equal to this guy. So it is not a finite union of the singletons, and it is not a countably infinite union of the singletons. The union we have right here is a union in which the index is a real number. The cardinality, so the index belongs to a set with cardinality small c, which is strictly larger than Lth node. So basically, what is the probability of this event? It's not defined. The axioms of probability theory tells you that you want to assign a probability measure to the elements of the sigma algebra, which are the subsets of big omega. You assign 0 to the empty set, you assign 1 to big omega, and you assign basically the sum of the probabilities to the finite or countably infinite union of disjoint subsets. So basically, from the axioms, this is not something that you can compute, right? So you cannot go from basically the premise, the starting point that the singletons are assigned the probability 0, and then say that then the probability of big omega is 0, because big omega is an uncountably infinite union. And so, guess what? You don't even have a tool. Basically, according to the definitions that we have, this is not this is not something that you can compute. Okay, because the union here is not on the natural numbers or any set that is equicardinal to the natural numbers. Okay, so here, what should we do now? Since the singletons are probabilities directly to intervals. Okay, so we will do this. We will basically make the probability of a given interval equal to the length of the interval. Okay, so this is the first thing that we will do. We will say, okay, we will take any interval AB. Okay, so it can be closed, it can be open, it can be closed from one end, and to all those intervals here, okay, we will assign a probability that is equal to the length of the interval, B minus A. And this makes sense if you want to make a uniform measure on the closed interval 0 to 1. So you want something like this. What is the probability that I will hit a number that is between 0.4 and 0.6? So you want this probability to be the length of the interval, to be 0.2. And of course, if this basically makes the probability of big omega, now in our case it is the closed interval from 0 to 1, so now big omega will be assigned the probability 1, as we should do. So what we will make this general. We will assign to each interval basically the length of the interval as its probability. And it won't matter whether we include the limit points of the interval. And the reason for this is that the singletons basically get the probability 0. So for example, this closed interval here is the open interval union the point A union the point B, and now those guys will be assigned the probability 0. So it won't matter whether we are talking about open or closed intervals. In all cases, we will assign the length as the probability. And you can think of length, and formally this is called the Lebesgue measure in one dimension. Okay, so then what else can we do? There is something that is that we think should be there in our assignment of probabilities, which is translation invariance. So if you are thinking of a uniform probability measure on 0, 1, which means that the likelihood of it hitting any number is the same, well, now what is the probability of getting something between 0.1 and 0.2 versus getting something from 0.4 to 0.5, something here and there. You may think that it should be the same, right? And this is captured, you know, that the length of the intervals is basically the same, right? So this shift, this translation of the interval should not affect our brain. It's like something in real life, like the length of an object, you know. So if you measure the length of the object, okay, you do not like expect it to change if you measure it on the left side of the room and then on the right side of the room, right? You think that the length will just be the same length, okay? So the second property, let's make this formal. So we want basically the translation invariance property, which means that let's suppose that we have a subset of big omega A, and let's assume that this subset is included in our sigma algebra. So we want the probability assigned to A to be the same as the probability assigned to A plus X. And A plus X is defined as basically you take each element in A and you add an X to it. You take each element in A and so you basically do a translation. Okay, you shift the set A by X. There is a point here, which is that what if when you shift your set A, some points get outside the closed interval from 0 to 1? In that case, what you do is that you fold those points back to the interval 0 to 1. So basically, A plus X is defined as the union. If A plus X is less than 1, we are good. Basically, we are still in the interval. But if there is an A in big A such that A plus X is greater than A, then we basically move it not to A plus X greater than A. So this is outside the closed interval 0 to 1. We will subtract 1. So we do wrapping, okay, sort of wrapping. Okay, so here is an example. If you take the interval from 0 to 0.75. So here it is from 0 all the way to 0.75, 0 to 0.75. Okay, and this is 1. Now, you want to basically add to it a number x from 0 to 1. Then basically, you know, 0, if you add 0 plus 0.5 will be 0.5. So this guy will move here, okay, and you go all the way there. Then the point 0.5 here will go to 1 because you are adding 0.5. But those guys here, if you add 0.5, you will get greater than 1. So what you do is that you subtract 1. And so this part will come here and go from 0 to 0.25. So you do wrapping so that, I mean, it's just a technicality, so that we remain inside the closed interval 0, 1. So here I mean by translation, so it is translation but with wrapping so that you never basically go outside 0 and 1, okay? So it seems that these two things are, you know, what you want, like you want to assign probability for intervals, okay? There are many subsets that are, you know, different from intervals, but for intervals at least, we want the probability to be the length, and we want the translation invariance property, which means that, you know, the length should not, the length of a, you know, which here it will be the probability assigned. The probability assigned should not depend on a translation, because we are trying to construct quote unquote a uniform measure, okay? So the secret here is uniform, okay? So definitely translations should not impact our probabilities, okay? So we have these two things, and of course there are, you know, there are the points we have from the beginning, which are basically the singletons are assigned a probability of 0, and so automatically all finite and countably infinite collection of disjoint singletons will be assigned the probability 0. Okay. So now we will prove something. So again, these two things, they are sort of like, you know, the first point and second point, what you want. Now we will show that it is impossible. It is impossible to satisfy these two if we insist on choosing the power set of big omega as our sigma algebra. Okay, so you know, suppose that you have this is a measurable space, right? it is basically the interval from 0 to 1. And then as a sigma algebra, you may choose the power set, which is basically the set of all possible subsets of, the closed interval 0 to 1. So if this is your sigma algebra, the power set, then guess what? It may seem surprising, but yet you will not be able to satisfy 1 and 2 while basically using your power set as your sigma algebra. Okay, so this is different from the cases in which big omega is finite or big omega is countably infinite. At the beginning of the previous lecture, I said, well, if big omega is finite or countably infinite, you can just use the power set as your sigma algebra, and you don't even bother about doing a selection of subsets or anything. You just take all possible subsets, and that's it. But here, when we talk about uncountable, basically sample spaces, this is just one impossibility theorem. There is actually a bunch of those guys telling you, if you want things to make sense, then you have to let go of the power set as your sigma algebra. You really have to do a selection. Okay, so you really have to do a sigma algebra that is not the power set. You need to make choices regarding the subsets, because some subsets are, of an uncountably infinite set are really evil. Okay, so we'll see this. So this is, we'll just take one impossibility theorem here, okay, but you will get the sense of what I am talking about. Okay, so, as you may expect, we will do a proof by contradiction. And so we will first construct a subset of 0, 1. And to construct this subset, I will call this subset set V, first letter of Vitali. And so basically this, Vitali was an Italian mathematician, and, he came up with, those examples for non-measurable sets, okay, which again is a surprising result. You may not think that something like this may happen, but it happens. Okay, so what is our set V? So we will make use of basically the partition of the real numbers that I talked about last Tuesday during the tutorial session. So basically, remember, I will review it quickly. So we have the set R can be written as a union. So you take basically the rational numbers. Okay, you take the rational numbers, and then you take some irrational number. Okay, so maybe you take pi, and then you put this set here. And what is this set? Basically, this is the set in which you have pi added to all possible rational numbers. Okay, so you take an irrational number, and then you add to it all possible rational numbers, and then this is another component of the set of real numbers. And definitely, basically the cardinality of this guy's LF node, because basically the number of elements here is equal to the number of the rational numbers, which is equal to the number of natural numbers. So that's LF node. Of course, these two guys together will not exhaust the set of real numbers, and so you go and choose another irrational number that is not here, another rational number that is not living here. Let's say square root 3, and so you take square root 3, and then you do the same. So basically, this is the set square root 3 to which you add every possible rational numbers walking on Earth, and then you continue doing this till you exhaust the set R. Okay, so basically each of those sets is characterized by the property that the difference between two numbers is a rational number. The difference between two numbers. So basically, if you go to this set here, if you take the difference of two elements of this subset of R, then pi will cancel, and you get the difference between two rational numbers, and the rational numbers are a field. So basically, they are closed under addition, and this means that the difference between two rational numbers is always a rational number. So each set here basically is characterized by the difference between any two of its elements being a rational number, and you can show that basically the difference between elements in different sets is not irrational. It's an irrational number. And the last thing I said during the tutorial session is how many of those guys do we have? So each one of them has a cardinality Elif node because each one of them has a number of elements equal to the rational numbers. So we said that basically we have an uncountably infinite collection of those guys. And the reason is that according to homework 1 problem 1, if you have a countable union of sets with cardinality Elif node, then the union will have a cardinality Elif node, but this contradicts the fact that R is uncountable. Okay, so we must have basically those subsets. If you want to index them, then you will have to use an index that is a real number. You cannot use an index that is a natural number. Okay, so this is the story here, that we will basically divide R into those P's. Okay, so these are basically sets. Each set, the difference, if two elements are in the same set, their difference is a rational number. If they are in different sets, the difference is an irrational number. Okay, and now here is how we will construct set V. Okay, so from set V, you will go to each one of those guys. So you will visit each one of those guys, pick an element in the closed interval from 0 to 1. And this will be our set V. The only constraint is that when we visit the set of rational numbers, we will avoid taking 0 with us. Okay, so from the set of rational numbers, choose any rational number from 0 to 1, but exclude 0. Don't take 0. From any other set, search for basically a number that is on the closed interval from 0 to 1. Okay, so for example, from this set pi, you may take the number pi minus the rational number 5 over 2, right? So pi, if you subtract 5 halves from pi, you will get a number from 0 to 1. So you may choose this number. Okay, so it's not important exactly what number do you choose. So actually, there is a huge, there is an infinite number of V sets that you can construct. We will just construct one of them. Okay, so so our construction is that we will basically from each one we will take a number. Just exclude 0 when you choose a rational number from 0 to 1. Note that set V, it has only one rational number, which is the rational number that you pick from this guy here. All other numbers will be irrational numbers, and all of them definitely by construction will be in basically the closed interval 0 to 1. Okay, so this is our set V. This is our set V. Okay, and now remember that we are operating under the assumption that we have the power set as our sigma algebra, right? In other words, that every subset of 0, 1 is feasible, and every subset should be assigned the probability, right? Because this is the probability measure is a function from the elements of the sigma algebra to basically the closed interval 0, 1. And so, basically, since now the sigma algebra is every subset, then we are saying that we should be able to assign a probability measure to every subset of 0, 1. Okay. Now we will basically construct from the set V. We will construct another set, which is V tilde. So what is V tilde? So V tilde is a countable union of translated versions of V. So what we will do is that we take the set V. So what is the set V? Set V again, it is an uncountably infinite set. Okay, it's an uncountably infinite set that was constructed by going to the partition of R, and from each, basically, each subset in the partition, we took one element, avoiding 0 from the set of rational numbers. So this is a set V, and what we can do is that we can take V and shift it, or translate it with wrapping, of course, and so we can add to V Q. So we can take V and add to Q. So we'll actually shift V plus Q and then union this over all possible rational numbers. So basically Q is a rational number in 0, 1. 1 excluded. So here we will basically take V, add to it a rational number from 0 to 1, 0 included, 1 excluded, from the union of all those guys. So that's V tilde. Okay. So what is V tilde? And what is its probability measure if it is a subset of 0, 1? Okay, so let's now investigate these things. Before doing so, let's remember our two desired things. We want the probability, we want the probability of intervals to be the length, and we want the translation invariance. We want translation invariance, which means that if you have a set A, if you shift this set by a number from 0 to 1, then you want the probability not to change, okay, because we are trying to construct a uniform measure. Okay, so now let's see basically what we have. First thing, you can show that the set V tilde, so V tilde is this thing that we have here, this union, this countable union, you can show that it is exactly equal to the open set 0 to 1. Okay, it is exactly this set that we have here. Okay, so the proofs of these, this claim and the next claim, the proofs are basically in the notes. You can read them if you wish. You can skip them if you wish. Okay, so V tilde, you can show that it is basically the interval from 0 to 1, 0 excluded, 1 included. This is V tilde. And so it is an interval, and it goes from 0 to 1. And so according to what we desire, we want to assign to intervals probabilities equal to their length. So basically the probability of V tilde should be the length of this guy, which is 1 minus 0, so it is equal to 1. Okay? So this is the first thing. But we can compute the probability of V tilde in another way. Why is that? Remember, V tilde is the union of V translated by Q with wrapping, of course. So if you go outside 0, 1, you subtract 1 to remain inside, and you take all possible rational numbers, right, that are from 0 to 1, like this, right? So this is basically an index that goes through the rational numbers, and it is a countably infinite index. So we can apply the axiom of a probability measure. If we know that those guys are disjoint. Okay, so you can say that the probability of the union is the sum of probabilities if you basically show that this, each one of those guys are disjoint. So it turns out, this is my second claim, that yes, they are disjoint. And again, you can see the proof in the notes. Okay, so basically, if you have Q1 not equal to Q2, then the set V plus Q1 intersection V plus Q2 is actually the empty set. It is empty. Okay, so because those basically sets involved in the countable union are disjoint, then you can apply the rule. The rule tells you that the probability of the union is the sum of probabilities. Okay, so the probability of the union will be the sum of probabilities. And then remember that, if you want to have a uniform measure, we want translation. It makes sense to insist on having translation invariance. So translation invariance, it tells you that if you take a set, which here is V, and this set, under our assumption that our sigma algebra is the power set, it is an element of the power set, so it is an element of the sigma algebra, so we should assign a probability to it. And the probability assigned to V will basically be the exact same probability to any of those guys. So this is equal to the probability of V for every Q, right? Because, each one of those sets is just V translated, okay? And we want a translation invariance, okay? So, if we want translation invariance, this summation will be the sum of a single number, right? So what should be the probability assigned to set V? If we assign a positive, probability can be positive. If it's a strictly positive, if you assign to V a strictly positive probability, 0.1, 1 over a trillion, whatever, then the problem is that, if you do this summation, the probability of V tilde will be infinity, which is rejected. So we cannot assign to V a probability that is strictly positive. Remember that, V tilde, from the first claim, it is actually part of 0, 1. It is a subset of 0, 1. Okay, so, you cannot assign to it a probability infinity. You cannot assign a probability greater than 1. So you may say, well, then we will assign to V the probability 0. That's the other option. It's either you give it 0, like what we did to the singletons. You either give a strictly positive probability or you give a 0. So if we give a 0, here is the problem. If you sum 0, 0 plus 0 plus 0 plus 0, you will get a 0. So the probability of V tilde will be 0. But V tilde is an interval, and it goes from 0 to 1, and so its probability should be equal to 1. So we have a contradiction. Here, okay? So again, you construct set V, okay, or let's basically tell the story again briefly. So you take R, again, there is a standard partitioning of R, okay, that you take R, you write it as, the rational numbers, union, then you take some irrational number, here I took pi, and then this is not just pi, this is basically pi to which you add every possible rational number. Then you have E, then you have a square root of 2, then you have all, those guys till you exhaust R. And what you do basically is that you visit each one of those guys. So you go to Q, you go to the rational numbers, and you pick a number between 0 and 1. Just don't take 0. Take any rational number from 0 to 1. Then you go to this set and pick a number. You go to that set and pick a number. All the numbers should be between 0 and 1. Now you have constructed set V. Then you construct set V tilde. So V tilde are basically V tilde is constructed by translating V by all possible rational numbers from 0 to 1, 1 excluded, and then having the union. Now V tilde, you can show two things. You can show that V tilde is 0 to 1 with 0 excluded, and hence, it's an interval and its probability should be 1. But also V tilde is a countable union of sets that you can show that they are disjoint. So the probability of the union should be the sum, and the sets involved are basically translations. And so if we want translation invariance, then basically all of those guys will have the same probability. Then regarding V, you can assign a positive probability, but this will make the probability of V tilde infinity. So this is something that is not accepted. And so we assign a probability 0 to V, and in that case, probability of V tilde will be something that makes sense. It is 0, which is a valid probability, but it contradicts the fact, that V tilde will be equal to 1. So the conclusion is that we cannot satisfy these two properties here, okay, that the length of an interval is its probability and translation invariance. We cannot basically do this in a consistent way, in a mathematically consistent way, if we just allow every possible subset of the closed interval from 0 to 1, which means that if we use the sigma algebra as the power set. So again, if you use the sigma algebra as the power set, then every subset is possible, and in fact you are under obligation to assign a probability to every possible subset of the closed interval 0, 1. But then you will get a contradiction. There are subsets of 0, 1 that are, you may think of them as evil. They cause you trouble, something like set V here. Okay, you don't know how to deal with this set. You assign probability that is positive, then you get V tilde, which is a subset of 0, 1, gets, the probability will be infinity, which does not make sense. But if you assign 0 to V, then you get a 0, but actually V tilde, its probability should be 1, because you can also show that it is the interval from 0 to 1. So that's, that's a problem. And hence there are, basically the way out is to say, actually something like V should not be included in our collection of subsets. Okay, so we need now something that is strictly smaller than the power set of 0, 1, and use that thing as our sigma algebra. Okay, so there are basically troublesome subsets. There are actually so many of these, and it's just excluded. Avoid using them. And here again we find ourselves like basically in a situation which the power set is not feasible if you want to do things in a mathematically consistent way, right? Mathematically consistent way, it means that for every event you assign a number as a probability. You cannot say that the probability of that event, if I calculated it in this way I get a 1, and if I calculated that other way I get a 0. Okay, this should not happen. A probability measured by the end of the day is a function, and in the function you should assign just one number. Okay, so V tilde should either have 1 or 0 or something in between. But if you basically include a set like set V, then you find that actually V tilde, you can make an argument and make the probability equal to 1 or 0. So we will just let this cannot happen. It will mess up your basically your probability. And so what we do is that we will use a subset of the power set. So our sigma algebra will not be the power set. Now, you may basically say that our contradiction may be resolved in a different way. Maybe actually the error is that we can construct set V. So how did we construct set V? We basically went to this uncountable union, and from each set we obtained an element living in 0, 1. Okay, so this is supported, there is no rigorous argument, why this should be feasible. So it is taken as an axiom. So basically, at the heart of math, we know that basically mainstream mathematics, it's based on an axiomatic system, the Zermelo-Fraenkel system, with the axiom of choice. So we have something called the axiom of choice, which tells you that if you have a collection, and this collection can be an uncountable collection of non-empty sets, then you are able to choose from each one of those sets one element. It seems to be very intuitive, right? So you have a collection, this collection may be an uncountable collection of sets. Each set is non-empty, so each set has at least one element. Then you can pick an element pick exactly one element from each set. It seems to be something that is very intuitive, but here is the price. If you accept the axiom of choice, then you can construct something like V, and then you will have to face the consequences, which is that there are subsets, of your sample spaces to which you cannot assign probability or measure in general in a consistent way. Okay, so basically the existence of sets that are non-measurable is, it comes from accepting the axiom of choice. So you may actually say, well, maybe we can just say that the problem in this proof is V. We cannot have V because we will reject the axiom of choice. You can do that. It's not how mainstream mathematics work. You can do that, but the problem is that the axiom of choice and its equivalence. So basically, there are several mathematical statements that are equivalent to the axiom of choice, like Zorn-Lena and others. Those are needed to prove many fundamental mathematical results. So basically, there will be a huge disruption if you just say, we'll not take the axiom. So one of them, that every vector space has a basis. This statement, you typically take it for granted. If you are dealing with any vector space, you just assume that there is a basis. There is a proof for that, and the proof for that relies on an equivalent to the axiom of choice. And there are other basically important results that require the axiom of choice. So to make the story short, basically mainstream mathematics will allow the axiom of choice. Okay, so the axiom of choice tells you that from perhaps an uncountably infinite collection of non-empty sets, you can choose one element from each set. This will allow us to construct basically set V, and combined with choosing the sigma algebra as the power set, we will reach the conclusion that there are, set V is problematic. It will cause problems when we assign probabilities. Okay, so this is basically the story. Okay, so the price of accepting the axiom of choice is the impossibility theorem that we have here, and there are several versions. I mean, because you may say, well, maybe actually the problem is that we insist on having a uniform probability measure. Maybe if we don't use a uniform probability measure, then our lives will be like okay, and we can use the power set. No. Okay, so it is something that is fundamental, and this is again the story of uncountable sample spaces. Uncountable sample spaces, you have to do a choice. You cannot use the power set as your sigma algebra, and this is the motivation for the sigma algebra. Remember, so in lecture 1, I told you, you may think, okay, so why even we do this collection? Why do we select, subsets? Why just not use them all? Well, because there are situations in which you cannot use basically all the subsets, else you get contradictions. Okay. So when you deal with omega, that is the real axis or a subset of the real axis, like the closed interval 0 to 1. So, okay, so we'll not use the power set because it may lead to trouble. We will use it. So we'll simply try to avoid those evil subsets like set V and the likes. So what should we do? So there is a standard sigma algebra that is used, and this will be the focus, of this course. It's called the Borel sigma algebra. Borel sigma algebra, and it is a sigma algebra that is constructed on the real axis from all open intervals of your choice. Okay. Note the following, that the Borel sigma algebra is not just the open intervals. You construct it using the open intervals, but it includes everything of practical interest and much more. Okay, because it's a sigma algebra, right? So remember, what is a sigma algebra? So you need to include the empty set. If you include any set, you need to include its complement. So if you choose in your Borel sigma algebra the open AB, so basically this is the open interval from A to B, which is this guy, then you are under obligation to choose also the complement. So you need to choose basically this guy here from -infinity to A and from B to infinity, right? So remember, sigma algebras are sigma algebra. I mean, they are not arbitrary, right? They have properties and they are closed under complementation. If you choose something in your sigma algebra, if you choose a subset of big omega in your sigma algebra, you must choose its complement. And if you choose a bunch of subsets, right, then you need to include their, their finite or countable union. Okay, so basically, basically we say that the Borel sigma algebra is constructed, or the technical word is generated. It's generated by the open intervals, but this does not mean that it only includes the open intervals. We will verify actually that it includes everything of that you typically use in probability, and some bizarre subsets of R that we'll talk about. Okay, so the Borel sigma algebra is sort of a tiny subset of the power set of R. It's a tiny subset. Its cardinality, you can show it's a very, you find this in books like on measure theory. Its cardinality is equal to C, while basically the cardinality of the power set of R is 2 to the C. So basically this is a tiny collection of subsets, but again, it's more than enough for practical applications. Now, this Borel sigma algebra, here is the nice thing. If you find the Borel sets, so those are basically the elements of the Borel sigma algebra. If you find them on R, on the real axis, how do we find them on 0, 1? Okay, then there is a trick here, which is you can define the Borel sigma algebra on any interval by simply taking the Borel sigma algebras, the Borel sets, by taking the Borel sets on R and intersecting them on A. So if you want a Borel sigma algebra on the closed interval 0, 1, what do? You take the Borel sets on R and you just take their intersection with 0, 1, and you will get basically the Borel sigma algebra defined on basically the closed interval from 0 to 1. Now you may ask, I mean, are we sure that when we do this intersection that we indeed get a sigma algebra? The answer is yes. It is in the notes on sigma algebras. There is something called the trace sigma algebra, and it is basically what I'm talking about. If you have any set, let's call it big X, okay, and you have a sigma algebra defined on that set. Now, if you choose a subset of X, let's call it A. Now, if you intersect everything in the sigma algebra with the subset A, then you will get a collection of subsets. You can show rigorously that basically this collection is a sigma algebra on A itself. Okay, the proof is, it's optional. So you may just take this for granted. Okay, so for granted, again, if there is a sigma algebra defined on some set X, you choose some subset A of big X, and then you basically intersect the sigma algebra with A, every element in the sigma algebra with A, you get a collection of subsets of of A and big X. Those basically are a sigma algebra on big A. And again, you can show that basically the collection satisfies everything related to sigma algebras. Okay, so let's go back to the sigma algebra on R again, and let's try to answer some questions. I mean, so what we are sure of is that this sigma algebra contains the open intervals, but does it contain the singletons? right? Does it contain closed intervals and so on? Yes, it includes, again, everything you may think of is there. In fact, it is difficult. It is actually very difficult to give an example of a subset of the set of real numbers that is not a Borel set. Okay, so non-Borel sets are very difficult to find. Anything that comes to you is with probability like 0.99999 is a Borel set. Okay, so let's do some verifications, like to make sure that for example, that the singletons are Borel sets. Okay, so remember our Borel set, what we can take for granted is that our basically Borel sigma algebra, it contains all possible open intervals on the real line. So does it contain the singletons? Well, let's take this. So you are interested in some point x, which is a real number. Now you can have this open interval. So there is a v, which is a natural number. So v is 1 or 2 or 3 and so on, and then you can have this open interval. So basically this is x. Then you can have an open interval going from x minus 1 over v to x plus 1 over v. Okay, so if v is 1, this is from x minus 1 to x plus 1. If v is 2, then this is x minus 1/2 to x plus 1/2, and so forth. So you have those open intervals. Each one of them, you can say by definition, is part of your sigma algebra, the Borel sigma algebra, because the Borel sigma algebra, we said that you can take for granted that it contains all open intervals. Now, what if you do an intersection of all those open intervals, basically sweeping v over all natural numbers? So the claim is that if you intersect those intervals, then you will basically get the singleton, which is x. Okay, so why is this the case? Note the following, that basically those guys here, so there is one guy that looks like this. It's an open set from x minus 1 to x plus 1. Then there is from x minus 1/2 to x plus 1/2. Then there is an open set from x minus 1/3 to x plus 1/3, and so on. Okay, so you'll find that x is living as the midpoint of all of those guys for every v that is a natural number. Okay, and then the intersection includes no other point. The intersection includes no other point except x. It's only one point. And why is this true? So for example, does the intersection include the point x plus 1 over 100? Does this intersection include this point? No. Why no? Because you are intersecting those intervals, right? So, those intervals, v, if you make v greater than 1, so there is an interval here that is x minus 1 over 1000 to x plus 1 over 1000. Okay? And so basically this guy here is outside this interval. And if it's outside this interval, then it is outside the intersection, right? So basically, if you take any point other than x, you can find an interval indexed by v that is with a value of v that is high enough such that the point is excluded from the intersection. Okay, and that's the reason that those intervals are designed basically to get smaller and smaller and smaller. Okay, so basically the intersection is just the point x. Okay, then what? So what is the conclusion? So each one of those open intervals, you can say by definition, are parts of the Borel sigma algebra because it includes all open intervals of basically on the real axis. And from the properties of a sigma algebra, we know that the sigma algebra contains all finite and countably infinite unions and intersections of its elements, right? So each one of those guys is in the Borel sigma algebra by definition, so the countable intersection is there, and so yes, we have the singletons. Every real number, alone is basically in the Borel sigma field. And if any real number is in the sigma field, then all finite subsets of R and all countably infinite subsets of R are already there, right? Because you can take, the real numbers, the singletons, and by the rules of a sigma algebra, basically you can have basically all the countable, all the finite and countably infinite unions and intersections are there. So, for example, the rational numbers are there. Why? Because the rational numbers are basically a set that is countably infinite. Okay, so it is there. So the Borel sets include again every finite or countably infinite subset of R that you may think of is there. The singletons are there, and every finite or countably infinite, basically, collection of the singletons will be there. So all those guys are with us in the Borel sigma algebra. Okay, so no worries. And all types of intervals, so I said something like this. So for example, if you take the closed interval, well, the closed interval is an open interval. Okay, so this is in the sigma algebra, in the Borel sigma algebra by definition, and then the singletons are there. So you can basically take the open interval and combine it with its endpoints, those two singleton subsets of R, the singleton subset containing A and the singleton subset containing B, and you union the three guys. And so that's a finite union. So we are guaranteed to have this finite union in our Borel sigma. So basically the closed intervals are there. So again, I emphasize that everything that that is of sort of practical interest. So typically, like when we compute probabilities, we compute them on intervals, unions and intersections of intervals, and so on. And so we do compute the probabilities, sometimes on basically integers, rational numbers. Every one of those guys is a Borel set. So if we don't use the power set of R and we just use the Borel sigma algebra, we are fine, right? We are not basically we are avoiding the problems of subsets of R like V, but we have everything of practical interest. The Borel sets also include what you can call bizarre, or weird subsets of R. So let's take one of them, the Cantor set. So here is how we construct the Cantor set. This is one version. Okay, so there are so many Cantor sets. This is one of them. So you start with the closed interval from 0 to 1. Okay. Then you take the open interval from 1/3 to 2/3. So this is the second third. Okay. So these are the elements that are strictly greater than 1/3 and strictly less than 2/3. And then we remove this. Okay, so we remove this. Okay, so our second step of construction will start with something like this. So we have from 0 to 1/3 inclusive, from 2/3 to 1 inclusive, but then numbers strictly greater than 1/3 and strictly smaller than 2/3 are gone. Then for each segment here, we repeat the trick again. So we remove basically the middle third from this segment and from that segment. So now we have 4 segments as shown. And then we do this again and again, and again, and again. We do this ad infinitum. And this is the remaining points. The remaining points are basically the Cantor set, the so-called Cantor set. Okay? So this is how the Cantor set is constructed. And one thing you may ask, well, maybe we are left with nothing in the end. The answer is no. You can show that the endpoints are always with you. They will never go away. So 0 will always be with you. 1, 1/3, 2/3, 1/9, 2/9, 7/9, so on. This point here, all endpoints will never be eliminated. So the Cantor set is definitely not an empty set. In fact, the Cantor set has an uncountably infinite, basically, number of points. So the cardinality of the Cantor set is actually C. You can show that there is a bijection between the Cantor set and the closed interval 0 to 1. Okay, so one of those, not so intuitive things, So you have the Cantor set, so you go to 0, 1, and you keep eliminating parts of this interval. You end up with a set that can be put into a 1-to-1 correspondence with 0, 1. And so basically the Cantor set, again, its cardinality is equal to C. Okay, now the question is the Cantor set a Borel set? Is the Cantor set a Borel set? And again, we show that something is a Borel set if we can construct it by applying complement, finite or countably infinite unions or intersections to open intervals. If you can show that the set can be constructed as such, then what you have is indeed a Borel set. It's part of the Borel sigma algebra. Okay? So basically, the idea here, or the trick here, is to think about the complement of the Cantor set. So to think about the parts that we remove, that we eliminate, right? Because at the first step of construction, you remove the open interval from 1/3 to 2/3. So here I'm not talking about the Cantor set, I am talking about its complement, whatever is removed. Then, in the second step, we remove 1/9, the open interval, 1/9 to 2/9, and also 7/9 to 8/9. Then, in the third step, we remove those guys here. Okay, so I think this would be like 1/27, 2/27, and then you go on. Okay, so those are basically, so you can think of the complement of the Cantor set as a union. You can show that this union is a countably infinite union of open intervals. So again, by definition, open intervals are there in the Borel sigma algebra. And now the complement of the Cantor set can be written as a countable union of those open intervals. So the complement of the Cantor set is guaranteed to be in the Borel sigma algebra. Now, since the Borel sigma algebra is a sigma algebra, if it contains a set, then it must contain its complement. So the Cantor set itself is in the Borel sigma algebra. Okay, so it is a Borel set. It is a Borel set indeed. Okay, here is what I'm doing. I'm basically trying to say that it is a countable union of open intervals, and hence it is a Borel set. Okay. Now the counter set is part of this interval, right? So let's go back to the uniform probability measure. Now if you assign a probability, so it is a power set, so it is in our sigma algebra. Okay, so now as a sigma algebra on 0, 1, we will not use the power set, we will use the Borel sigma algebra, and the counter set is part of the Borel sigma algebra, so it means that it has a probability, right? Because again, remember the probability measure is a function from the sigma algebra to 0, 1. So basically, if any guy is living in your sigma algebra, you need to assign to it, a value, a probability value from 0 to 1. So what is the probability of the counter set under the uniform probability measure? Okay, so again, this is a situation in which it may be easier to work with the complement. So in the previous lecture, I talked about the properties of a probability measure. So remember, the first property was that basically the probability assigned to the complement of an event should be 1 minus the probability assigned to the event. This property is very nice, and not just in our example here. In many cases, sometimes it's just much more convenient to think about the complement event. So here, let's talk about what is the probability of this guy under the uniform measure, because this guy is a subset. So this guy is a subset of 0, 1, and it is now it's an element of the Borel sigma algebra defined from 0, 1, because it can, because of the story that we talked here, that basically its complement can be written as a countable union of open intervals. Okay, so what is this probability? Okay, so let's go here, to the complement. And the complement can be written as this union, and it's a countable union, and so we can write the probability of the union as a summation. Okay, so here it is. It is a summation m from 1 to infinity, 1 over 3 to the m. Okay, so let's explain this first. So let's see the length of the intervals that we remove in our construction of the counter set. Okay, so at the first step of construction, we remove this open interval from 1/3 to 2/3. And what is the probability of this interval? You remember, uniform measure, the interval takes the probability that is basically equal to the length. Okay, so the length is 1/3. Now, in the second step of construction, we remove these two guys. Okay, each one of them is 1/9 in length, then 1 over 27 in length, and so on. So basically, 1 over 3 to the power m, this is basically the length, hence the probability of basically the open interval that has been removed during the nth basically step of construction. Okay, but note that when we do the removal, at the first step we remove one interval, in the second step we remove two guys, in the third step we will remove basically this 1, 2, 3, 4, the middle thirds from these 4 segments, and so on and so forth. So basically the total number of intervals removed during the nth step of construction, you can verify that it is 2 to the m minus 1. So if m is 1, 2 to the 0 is 1, we remove just the middle third of the closed interval 0, 1. Then when m is 2, this guy will be 2 to the 2 minus 1, so it's 2 to the 1, it's 2, because we remove the intervals 1/9 to 2/9 and 7/9 to 8/9 and so forth. Okay, so This is the sum of probabilities, and those intervals are disjoint, so the probability of the union is the sum of probabilities. Okay, so this should be, according to our rules, this should be the probability that is assigned to the complement of the Cantor set. And what you do is that you take 1/2 as a common factor, and then you are left with a geometric series. And then basically you apply the formula for the geometric series. So here we go from 1 to infinity. So it's the first term divided by 1 minus the ratio of the geometric series, which is convergent here because 2/3 is strictly less than 1, and you get a 1. So the probability of the complement of the Cantor set is 1, and hence the probability of the Cantor set, or any set living, basically we now it's rule, it's a general rule. The probability of any set is 1 minus the probability of its complement, and so this is 1 minus 1, and so that's 0. So the probability of the Cantor set is 0. So if you close your eyes and you choose a number uniformly from 0 to 1, you don't give preference to any part of the interval from 0 to 1. So if you follow a uniform way of selection, then the probability of choosing the number that belongs to the Cantor set is 0. And of course, the probability of choosing a rational number is 0. The probability of choosing any number that belongs to a finite or countably infinite set is 0. But the nice thing about the Cantor set is that the Cantor set actually is composed of an uncountably infinite collection of points. Despite that, its probability is equal to 0. Now, something very important you need to keep in mind. The complement of the Cantor set, which is basically this union here, is not big omega, right? And the Cantor set is not empty. It is not the empty set, right? However, the probability of the Cantor set is 0, and the probability of the complement is 1. So again, for some reason, some people have this sort of idea that the probability is 0 for the empty set and is 1 for omega. It can be 0 for many other subsets of big omega. It may be 0 for many other guys in the sigma algebra that you define on your sample space. Same story for basically 1. The fact that an event has a probability 1 does not mean that this event is simply the sample space. No, it can be a proper subset of the sample space, and yet it has a probability 1. So, in fact, the probability of picking a number that is irrational on 0, 1, remember, the rational numbers can be written as a countably infinite collection of the rational numbers, the singleton subsets of R that are rational on 0, 1. So this guy, the probability will be 0 plus 0 plus 0. It is 0. The probability of choosing an irrational number is equal to 1, and so on and so forth. Okay, so keep this in mind that probability 1 does not mean that you are talking about omega, and probability 0 does not mean that you are talking about the empty set. This set is a huge, it's an infinite set, and yet its probability is 0. This is even larger. The cardinality of this set is C, and its probability is equal to 0. Okay, and those guys are definitely not big omega, but their probabilities are equal to basically 1. Okay, so keep this in mind. If an event has a probability 1, okay, so if probability of A is 1, okay, so we'd say that A occurs or happens almost surely. So we have this, we need to learn this term, almost surely, or with probability 1. They are basically the same thing, and almost surely AS, and with probability 1, WB1. So here I say that A occurs or happens almost surely. So this is just a way of saying that the probability of A is equal to 1. Okay, or I can write it that A happens with probability 1. Okay, so get used to these basically notations, or those guys here, they are used a lot. And so almost surely, again, the probability, or with probability 1. Of course, this one is clear regarding what it means, but almost surely is also used a lot in the literature and in references. So and again, never ever do this mistake and say, okay, something with probability 1, it should be big omega. This is not true. Okay, A does, if the probability is 1, it can be something that is fundamentally different from big omega. Okay. So okay.
You keep iterating that something has a probability of 1 and does not mean that it's a sample space. Is it because right now we're not talking about the probability in the sense that we used to study? It's because it's the probability measure.
No. This no. What I am talking, what I said in this lecture is exactly applicable to the uniform random variable defined from 0 to 1. In fact, in a previous course on probability, I'm sure that at least some of you know, or and you studied random variables and so on. So the uniform random variable U01. Okay, so U01 is basically the story I told in this lecture. Okay, so yes, if you choose, if you ask yourself what is the probability of choosing a rational number, 0. What is the probability of choosing an irrational number between 0 and 1? What is the probability of choosing an algebraic number? 0, because algebraic numbers basically have the cardinality elif node. So the probability is 0. What's the probability of choosing a number that basically belongs to the Cantor set? 0. Okay, what is the probability of choosing a number that is not in the Cantor set? 1. So basically, this is what we we will later start talking in terms of random variables. This will come shortly in the course, but this is the same. Actually, random variables are nothing but a transfer of probability measure from the sample space to the real line. Okay, so we will define them rigorously later, but what I have said is applicable to random variables. Actually, what I've said is true when it comes to all absolutely continuous random variables. Those are defined such that if you have a set of length 0, then basically they are assigned the probability 0. Okay, so this will come later. But yeah, what I'm saying is not abstract. It is something that is also related to variables.
Okay, thank you for the clarification, Doc.
Okay. Now there is something called conditional probability. And for conditional probability, of course, now we know the triple. Now we are friends with this, basically this triple of of a probability space, a sample space, and a sigma algebra defined on it, and then a probability measure. Now we choose B as an event. So an event is just, it means a subset of omega that is included in the sigma algebra, and let's choose a subset that has a strictly positive probability. Okay, now here is how we define the conditional probability of some event A. So again, when I say event, then I do not need to repeat the story. Event, it means that it is a subset of big omega, and it is a subset that is included in your basically nice collection of subsets, the so-called sigma algebra. Okay, so the probability of A given B is defined, so that's a matter of definition. So actually, you can put this triangle over the equal sign to mean that this equality is not something that we derive, it's something that we define. It's the probability of A intersect B divided by the probability of B. And of course, you can see from the definition why we insist that if we condition on event B, then we need basically the probability of event B to be strictly positive, because in the definition we divide by the probability of B. So if it's 0, we are in trouble. Okay, so we need basically to condition on an event, and this event should have a strictly positive probability. Okay, so this is how we compute the probability measure. Okay, when we condition on B. Now this way of computing probability. So now, the probability, if you apply to all the members of the sigma algebra, conditional B. So this thing, so here again, if we have A guy here, so let's call C and B, this is computed as the probability of the intersection over the probability of B, is indeed a probability measure. It's a new probability measure, right? So the idea is that you can start with some probability measure, okay, and then you can derive a new probability measure called the conditional probability measure, again by picking some subset that is in, that is in the sigma field or the sigma algebra, and such that its probability measure is not equal to 0, it's strictly positive, and we can define this new probability measure, which basically is computed by computing the probability of the intersection divided by the probability of B itself, which is this element that we condition on. And of course, you can play this game with any event with a strictly positive probability. So we want to show that actually this guy here is another probability measure. So this is our original probability measure. Then we can construct this new probability measure so long as under this probability measure B has a non-zero probability. How do we check that something is a probability measure? Probability of the empty set should be 0. So the probability of the empty set, so it's the probability of the empty set intersect B. The intersect empty set on and any subset of big omega is empty. And so this is the probability of the empty set. And so this guy is 0 and this guy is positive. 0 over a positive number is 0. So indeed, this new probability measure gives you 0 when we choose the empty set. What if we plug in omega? If you plug in omega, then again, you just follow the rule. This is how things are defined. So we take the probability, you take this guy intersect B. Now B is a subset of big omega, so the intersection is B itself, and we are dividing by the probability of B, so this is something positive over something positive, and this we get a 1. And so we are good, right? Because we want, if we want to say the word probability measure, it needs to satisfy 3 properties. We have now 2 of them, 2 of these properties satisfied. What if we have a connection, of disjoint, basically members of the sigma algebra? So what is the probability of the union I from 1 to infinity AI intersect B? Okay, again, this is, I will talk later about the practical meaning of conditional probability, but for now it's sort of like a definition. It's just a definition. Probability of an event, given some event with non-zero probability, just compute the probability of the intersection and divide it by the probability of this guy here. So we will do so, just use the definition, okay? And then if you have a union of sets, so this is basically A1, union A2, and so on. If we have a union of sets intersect one set B like this, you can show that basically this is the same as the union. So this is equal to, you take A1 intersected with B, then you union with A2 intersect B, then we union with A3 intersect B, and so on and so forth. Okay, and you can show this, it's not difficult. So basically this union intersect B is the union of each of those guys intersect B. Now note that this intersection here is a subset of AI, and the AIs are disjoint, right? When we check whether something is a probability measure, we take our subsets to be disjoint. So AI intersect B, those guys are basically disjoint, and so you can apply the rule that for the original probability measure, basically the probability of this union is the sum of probabilities, and so basically it is the sum like here. But then, each one of those terms by definition, so again by definition, is basically the probability of is the sum of probability AI given B. So you start with the probability of the union, sorry, here, this one here, let me change the color. So we start with the probability of the union given B here, and you end up with the additivity rule satisfied. So we have additivity, and so actually we have now satisfied the three properties of a probability measure. So conditional probability is sort of a new probability measure that you can construct using an already existing probability measure by applying this formula here. Okay, so this is for now. Again, seems like very abstract, but actually it's very useful. And like as a meaning, intuitive meaning will be, it is basically the probability of event A if we already know event B. But I mean, this will come perhaps in the next lecture. Okay, when we like solve examples and like have more practical feeling regarding conditional probability. Because conditional probability is a probability measure, then what do you expect? It has all the rules of probability measures. So, right? So just by proving that conditional probability is a new probability measure defined on omega and the associated sigma algebra, then everything that we showed basically in the previous lecture is applicable here. So definitely the probability of A complement given B is 1 minus the probability of A given B. This is true. The probability, the conditional probability is just a new probability measure. It has all the properties of a probability measure. So the sum of the probability measure applied to an event and its complement should be 1. So this will be true. If A is a subset of C, then the probability of A given B is less than or equal to the probability of C given B. Okay, again by the results that we learned in the previous lecture. Basically, inclusion, exclusion. So the probability of A union C given B will be the probability of A given B plus the probability of C given B minus the probability of A intersection C given B. So it's like the old guys, you just make everything conditioned on, you just make everything conditioned on B. This is the general